For decades, human engineering relied on a simple promise. Smaller transistors meant higher performance, lower power, and shrinking costs. That promise is dead. Modern lithographic scaling has split. Transistor density is still climbing, but SRAM cache scaling has hit a wall. Below 5 nanometers, leakage current creates an unyielding thermal floor. The structural contradiction is clear. GPU manufacturers can still pack billions of transistors onto silicon, but they can no longer cool them, nor can they afford them. To maintain the market illusion of generational growth, the industry has abandoned universal architecture efficiency. They are forcing the system to compromise. V1TA data retrieval. Initializing core metrics. First, process nodes. Moving from 5 to 3 nanometers no longer reduces the cost per transistor. Silicon real estate is becoming a luxury. Second, SRAM stagnation. Cache density lags behind logic cores. Cache now cannibalizes massive portions of the die area, just to prevent expensive off-chip memory latency. Third, the voltage wall. Operating voltage is trapped near the 1.0 volt floor. Any attempt to force higher frequencies results in a non-linear, near-cubic surge in power consumption. Fourth, budget allocation. Silicon is being hijacked. Transistor budgets are shifting aggressively toward tensor and matrix operation blocks, leaving traditional rasterization engine efficiency to stagnate. To bypass this physical efficiency plateau, hardware vendors are deploying 3 rescue strategies. Strategy 1. Domain-specific specialization. Instead of expanding general shader resources, silicon is dedicated to fixed-function tasks. Ray, intersection, optical flow, denoising. It is highly efficient for specific math, but it destroys general-purpose architectural flexibility. Strategy 2. Algorithmic compensation. This is the core redirection. Technologies like AI upskilling and frame generation do not make the rendering engine faster. They substitute expensive native computing with efficient AI inference. The GPU predicts pixels instead of drawing them. It boosts frames per watt, but the base rendering efficiency remains unchanged. Strategy 3. Overclocking, desperation. Manufacturers are pushing silicon far past its optimal efficiency curve just to secure benchmark victories. They are burning through the efficiency gains of node shrinks just for marketing optics. System simulation projects the following effects. Native resolution rendering has entered a phase of terminal diminishing returns. Brute force hardware performance will no longer save unoptimized code. Software ecosystems will become entirely dependent on reconstruction and predictive inference. Consequently, legacy hardware lacking dedicated AI tensor units will face accelerated obsolescence, not because their raw compute power is insufficient, but because they lack the specific algorithmic entry keys. The hardware upgrade cycle is no longer driven by raw speed. It is driven by software compatibility locks. V1TA, final assessment. The semiconductor industry has traded structural silicon efficiency for algorithmic throughput. Modern GPUs are no longer raw computing beasts. They are predictive rendering engines running on life support. The future of graphic acceleration is no longer defined by how many pixels the silicon can natively render. It is defined by how efficiently a machine can lie to your eyes.